Hi there everybody, welcome back to another MCAT ACE lecture. And in today's lecture we are going to be working on part 2 of NMR spectroscopy. So just as a brief background, if you have not watched part 1 yet, we would strongly encourage you to go back and check that out before proceeding forward here, because some of the information in that first lecture series will pertain to what we're going to attempt to solve here. So for those of you that watched the NMR Spectroscopy Part 1 lecture, we went through the basic background of NMR spectroscopy, and we also talked about important concepts like the splitting of protons and nuclei, and then we also discussed things like chemical shifts. So that's all going to be considered background knowledge in this lesson when we get ready to start examining some more in-depth examples. So there's a couple of things here that we're going to want to take a look at. And if you look at this list, it looks rather small, but each one of these is going to go into quite a bit of detail. So the first thing that we discussed at the end of the previous lecture is that we want to take a look at examining some of the ppm trends. So when we get those parts per million that show up on the NMR spectrum, there are very oftentimes general trends that go along with where certain protons are most commonly found. So for instance, methyl groups, CH3 groups that are not near any electron withdrawing groups are almost always found around 1 ppm. So we're going to give some general ranges as guidelines, and that will help in predicting some of these structures as we move forward. So then the second thing we want to do here is predict a rough spectrum with splitting from a chemical structure. So in these examples, I'm going to put up and provide a general structure. It's going to be a pretty simple one, and then we are going to attempt to create or draw a rough sketch of our own NMR. And I do want to note, when we're doing this, you don't need to pinpoint the exact location of where the peaks are going to show up. So a general region is going to be appropriate, and on top of that, really just knowing which peaks would be further upfield or downfield is going to be of vital importance there. Then we are going to examine some spectra and compare those to the structures. So the first part there, we're taking some structures and trying to predict what the NMR would look like, and in the second part we are going to look at an NMR and compare it or draw some conclusions to different structures. And then finally, as usual, we will have our review questions, and we will wrap up with a summary of what we learned here. So to get started, let's take a look at ppm trends and some of the most common groups that you will find when solving for proton NMRs and where we would expect to find them along the spectrum. So, just as a brief reminder, when we're dealing with proton NMR, you would range all the way from 0 ppm, which is where you would have your reference standard, and then you can go usually up to about 12 ppm at the highest point. Now, if you have a carbon-13 NMR, this scale is much larger. You can go up to about 200 ppm. But by and large, we're going to be concerned with proton NMR when we're looking at these examples here. So, what are some of the common groups or trends? Well, at the beginning of this video, I mentioned that we can have CH3 groups, which are primary alkyl groups. So I'm just going to abbreviate primary like that, and alkyl. So a CH3 that's not attached to any type of electron withdrawing group, so in other words, there's no significant deshielding that would be going on for the nuclei. And those are going to be found in general anywhere from 0.7 ppm to 1.3 ppm. And again, this is a very rough estimate or guide. So if this methyl group is several spaces away from an electron withdrawing group, let's say 2 or 3 atoms away from an electron withdrawing group, then it might be a little bit closer to the 1.3 ppm because of some deshielding effects that are occurring 1 or 2 spaces down. All right, so then some of the other common ones, we would certainly have secondary alkyl groups. So a secondary alkyl group, and let's just put here in parentheses CH3, right, attached to whatever it might be. So for a secondary alkyl group, you're talking about a CH2 group that would be attached on both sides, most likely to other hydrocarbon groups. Okay, now this is going to be a little bit further downfield, and we're going to have 1.2 to about 1.6 ppms. Right? And then for a tertiary, the trend would continue. So for a tertiary alkyl group, now we're just talking about a CH group that would have 3 other bonds. So it would be 1, 2, 3, like that. And these groups get pushed down just a little bit further, so they're going to be about 1.4 ppm to about 1.8 ppm. What's important to note here is in the absence of any type of electron withdrawing group, these are all going to be a bit below, or significantly below if you're talking about the primary group, 2 ppm. So once you get to 2 ppm and above, it is usually a pretty solid signal that you have some sort of deshielding going on. And then that, depending on the type of deshielding and how strong it is, that can range all the way up to the 12 ppm range. But your general hydrocarbons that are not affected by oxygens, nitrogens, double and triple bonds, you're going to find those on the upfield portion, specifically above 2.0 ppms. All right, now, when we start to introduce some of these slight deshielding effects, we can see another jump in this type of pattern. So what happens if we have a carbon-carbon double bond, okay, and then there is a hydrocarbon attached to that? So this proton right here, the proton isn't directly attached to the double bond, but it's attached to a carbon that is attached to the double bond, right? Now, some people may be familiar with this term. This is known as allylic. Okay, this is very often brought up when we're talking about carbocation stability, because allylic carbocations are highly stable due to resonance. So allylic protons are going to be anywhere from around 1.6 to 2.2. So they can start to go a little bit north of 2. Again, we're not directly attached to the double bond, but we are starting to get a bit of deshielding effects in closer proximity to the protons here, instead of just regular hydrocarbon groups. Right? And then in a similar manner, we can get methyl ketones. And when we have a methyl ketone, we're talking about a CH3 group that's next to a carbonyl, right? And then there's some other remainder of the molecule over there we abbreviate with R. But this methyl group next to a carbonyl group, now we start getting some more deshielding going on. And so usually when we see something like this, the minimum is about a 2.0, and then these can start ranging all the way up to about 2.5 when you have methyl ketones, ppm. Right? So similar to this, when we start bringing in some more of these types of effects, if we have an aromatic ring and we have a methyl group on the aromatic ring, so this would be an example of toluene, okay? But anytime you have a methyl group, there could be other things on this ring, like hydroxyls or stuff like that. But anytime you have a methyl group that is directly on an aromatic ring, that methyl group is going to be anywhere from about 2.4 to 2.7 ppms. All right, so the general trend that we're noticing here is that the alkyl groups that don't have any electron withdrawing groups are the furthest upfield, and then when we have protons that are near some neighboring electron withdrawing groups, right, then we start to get a climb above the 2.0 mark. Now again, I want people to realize or keep in mind, right, let me just draw this down here, that when I have an aromatic ring, I'm not talking about the protons directly attached to the aromatic ring. We're going to get to that. I am talking about if you have a methyl group, these protons that are attached to this carbon, and this carbon is attached to this ring, which has the deshielding effects. So it's a bit different there than the protons being directly in contact with the deshielding effect. All right, so just keep that in mind as we're moving along the scale here. Now, after aromatic, we can start to look at any type of alkyne. So now we're talking about primarily a terminal alkyne, because if you had an alkyne that was internal, meaning it was a carbon-carbon triple bond without any sort of hydrogen terminating it, then that carbon-carbon triple bond would not have a proton on it. So in other words, we're looking at something like this. Here's the rest of the molecule, and then the alkyne terminates with a proton. So this proton right here would have a pKa of about 2.5 all the way up to 3, because we do have some more deshielding going on once we get up to this range. And now you're starting to talk about protons that are directly in contact with some of these groups that are doing the deshielding here. All right, now I'm going to move over to the right here and continue our list. So the next one that is widely found is alkyl halides. Now, when we're dealing with the alkyl halides, these can have a large range because you can have different halogens. So fluorine would be the most electronegative in withdrawing, and then iodine would be the least, so that can play an effect in this. But you're going to find anything in the range of 2.5 to 4.0. Now keep in mind that this is in reference to organic compounds. So we're talking about if there's a CH group and that CH group is directly attached to a halogen, which we'll represent with X here. Right? So this proton, if this proton is attached to a carbon that is directly attached to a halogen, which is a strong electron withdrawing group, you're going to be anywhere from the 2.5 to 4.0 region. Right? And in a similar manner, we can also deal with alcohols. Now, the oxygen is going to be more electronegative than some of those lower halogen elements. So the bromines, the iodines, things like that. Fluorine is still the most electronegative element of the bunch, but when we get to oxygens for alcohols, you're going to find a range of about 2.5 to 5.0. Okay, so again, when we're talking about an alcohol group does directly have a hydrogen on it. So we're talking about something that would look like this, right? So here's that hydrogen group right there. That's going to be anywhere from 2.5 to 5.0. Now, what if you have a proton that is directly next to the alcohol, right? So a proton like this that has an alcohol next to it, those can be anywhere from around usually 3.2 to about 4.5. And again, these are rough parameters. All right, so what happens if instead of an allylic, we have what's known as a vinylic proton? So a vinylic proton is going to be one that is directly attached to the carbon-carbon double bond. So now instead of there being another carbon here, this hydrogen is directly attached there, right? So this is going to push it up again, and we're going to be anywhere from 4.5 to 6.5 when you have vinylic. All right, so we're getting close to the end of the trends here in terms of the most common ones you're going to see. However, there are a few more that are very important to talk about. So if you remember, I was discussing aromatic a minute ago, and I said, oh, we're going to come to this example. So with the aromatic, when you've got the ring here, if you have hydrogens directly on the aromatic ring, there's going to be serious deshielding going on, and these can range anywhere from 6.5 all the way up to 8.0. And I will just note that the average that you're usually going to see these is somewhere around a 7.0 to a 7.3 ppm. Okay, so that's most common. One of the things that can happen here is when you start putting different groups onto aromatic rings, those groups can drastically affect where the protons are going to show up, depending on if the group that's put onto the ring is electron withdrawing or electron donating. That can play a very large effect on where you're going to find either shielding or deshielding going on. So then finally, if we come back around to the carbonyls, we already looked at the methyl ketone, but when we deal with a carbonyl that has a direct proton on it, we call that an aldehyde. And the aldehydic proton, so this proton right here, is going to show up anywhere from usually about a 9.5 to a 10.0. So we're getting very, very far into the deshielded region. We're going very downfield at this point. And then finally, the one other that is a carbonyl, similar to an aldehyde, but it's got another oxygen, is the carboxylic acid. And when we have a carboxylic acid group, which I'm abbreviating Ca there, these go from 11.0 to 12.0. So if you find anything really down past the, I'd say the 10.5 ppm range, getting closer to the 11 and above, then you're starting to look at carboxylic acid protons at that point. And that is primarily where you would find most of these common groups here. Some others that are kind of similar, so you can get nitrogens. So if you have an amine group, you have a nitrogen with a hydrogen. Amines are very similar to alcohols. Nitrogen and oxygen are not that far apart with electronegativity, so you'd expect an NH group to be in the same general sort of range there. But this should be a good guide and a general a guide. It should be something that you can look to when you're trying to make these types of predictions. So I'm going to go ahead and clear the board here, and we are going to bring up one or two examples where we want to do a rough sketch of what we would predict the NMR is going to look like. That's going to include splitting, approximate ppms, and then we would also talk about the integration. So let me clear the board and I'll be right back. Alright, so now we're going to move on to predicting some NMR spectra based on structures. So just to clarify, because you may hear the term spectra or spectrum, spectra is plural, whereas spectrum is singular. So each compound should have an NMR spectrum, but when we talk about predicting NMR spectra, it's just a plural form of that. We're saying we're going to be looking at multiple spectrums, quote unquote, when we're dealing with spectra. So the first example that I thought we should go ahead and take a look at, and again, we're going to keep these relatively simple here, is ethanol. So ethanol is the form CH3, CH2, OH. It's got plenty of protons to work with, and it also has some deshielding going on with different splitting patterns. So this is a very good starter molecule for us to examine. So the first thing I want to do here is I want to draw ethanol out in more detailed structure. Now, if this helps you, especially while you're practicing, I would encourage you to take the time and draw these structures out. However, you need to keep in mind that when you are in the timed exam, you are going to have a limited amount of ability to draw these structures out in terms of it taking up your time. So I would save it only in the cases where you really feel you need to draw it out and you're not comfortable with it. But while you're practicing, it might not be a bad idea so that you can grab a hold of some of these ideas when we're talking about shielding and deshielding and things like that. So what do we see here? Well, the way that we're going to break this down is we're going to analyze each little chunk, and then we are going to attempt to assign it somewhere along the NMR spectrum. So here is the first chunk. I've got a CH3 group, right? And I'm going to use different colors to switch back and forth between these so that it's very clear what we're working with. I then have a CH2 group here. So that's going to be the next chunk that I'm going to look at from a spectrum standpoint. And then finally, I've got my OH group. Right? So those are going to be the three major portions that I examine when I'm attempting to put together this spectrum. So let's draw a general NMR spectrum over here. Again, this should be a very rough sketch. We're not expecting anything that's going to be super intense here. So here's my 0 ppm mark, and then we're going to say right up here is my 12 ppm mark. All right, so we'll just put a 6 here in the middle so that we have a general rough estimate of where this stuff is landing. So let's start by taking a look at the CH3, the methyl group, okay, and then we'll work our way to the right. So there's a couple of things that we want to consider or figure out when we're looking at this methyl group. The first thing is going to be, what would the approximate ppm be that I would expect for this? So if you remember, and if you don't, go ahead and either look at your notes or go back to the video. I would suggest that you have what we just went through written down somewhere. The methyl groups, if they are attached to other hydrocarbon groups, and this one is, it's a methyl attached to a methylene or a CH2 group. And so I would expect that to be anywhere from 0.7 to 1.3, okay, on the ppm scale. So if I were to guess, because I do have an alcohol present here that's another space away, so there is some deshielding going on 2 spaces away, right, or 2 atoms down. So I'm going to say, let's move this somewhere just slightly above the 1 ppm mark, all right, and I'm going to mark it in red, just like the color we highlighted it with. So I'm going to say, let's say that this right here, right, is about 1.1 will be our best estimate. Again, rough estimates are fine here. So that takes care of one thing. We know that the ppm we're expecting is going to be about 1.1 ppm. Now, there's 2 other things we need to talk about. The integration, which I'm going to put the little delta sign there. Okay, the integration should almost always be the easiest thing, especially if you're looking at the structure. So the integration is going to be the total number of hydrogens that are accounted for in that methyl group, and that should be 3 hydrogens. So we would expect this signal, whatever it splits into, to integrate to 3, because that's the number of hydrogens that methyl group has. Now, when we look at the last thing, and we just mentioned it, we need to talk about the split. So how is this going to appear? Is it going to be a single peak? Is it going to be a doublet, a triplet, etc.? So remember, you can go into all the different spin states like we talked about in the first lecture where we were drawing the up and the down arrows. But that's going to take a lot of time if you're in the middle of your exam. So the best thing to do is use the n+1 rule. Okay, so we're going to come back to this here. So n is the number of neighboring hydrogens plus 1, and that's what our signal should be. Again, some people will get confused and they think that the number of splits has to do with the number of hydrogens. So if they see that there are, for instance, 3 splits, so they see a triplet, they think that that means it must be 3 hydrogens. The splitting has nothing to do with the current number of hydrogens for that signal. It has to do with the neighboring number of hydrogens and how they affect the spin. All right? So when we look at this, the neighboring CH2 has 2 protons. So 2 plus 1 is going to equal 3. So this would be a triplet, and we will expect a triplet to show up around 1.1, and that triplet should integrate to 3 hydrogens. All right, so that's the first peak that we've assigned there. The next thing we're going to do is go over to the CH2. So when we go over to the methylene group, all right, we have to look here. This is going to be next to the oxygen, right, and also the carbon. So now we have some serious deshielding going on, and we need to consider that with the ppms. So if you remember, when we were looking at alcohols, okay, specifically protons that are directly next to alcohols, we said they could probably be anywhere in the rough range of like a 3.2 to a 4.5. All right, so it can really vary, and we're not going to get into all the complications here. Some of it depends on the type of solvent you run your NMR in and hydrogen bonding and stuff like that. However, making a reasonable guess or estimate is acceptable here. So let's go ahead and say at 3.5, we will expect to see this CH2 group. All right. So we are going to place a mark. Again, I'm trying to estimate this here. We'll even say, let's go ahead and bump it up and say like 3.7. Okay. So the question then becomes, if I've got this right here, it's going to integrate to what? That should be easy. That's 2 hydrogens that the CH2 contains. And now again, you can see with the split here, right, when I do the split, that this is not just going to be a doublet because there's 2 hydrogens. I need to look at the neighboring hydrogens. So I'm looking at how many hydrogens are present in this methyl group. And there are 1, 2, 3 of them. So 3 plus 1 is going to equal 4. So there's a quartet in this case. And that's what I would expect to see. I'm going to see a quartet that integrates to 2 hydrogens. Okay. And just a note here, a lot of students will say, well, what about the hydrogen with the alcohol here? Because this electron withdrawing group is deshielding, severely deshielding the nuclei around it, this CH2 cannot feel the effects of anything on the other side of that oxygen to a great extent. So this hydrogen right here is going to not affect the split. This one right here is not going to affect the split of the CH2. And vice versa. When I look at the alcohol hydrogen there, it will not end up having any type of splitting due to the CH2. The CH2 will not play an effect on it. So that brings us to the alcohol. That's the last piece here. Okay, the alcohols can widely vary in terms of where we find them, anywhere from like a 2.5 to a 5.0. So again, that's something that you would look at on a case-by-case basis as it comes up. But what we're going to do is just make our best guess right here. And let's go ahead and say that the alcohol is going to show up at 4.5, which we'll mark right here. Okay. The important thing is where we're seeing this, and especially that the CH3 group is further upfield or closer to 0 compared to the others. So we'll say that this has about a 4.5 ppm, and then it's going to integrate to 1 because there's only 1 hydrogen associated with the alcohol. And then the split, okay, again, the CH2 will not affect it because of that oxygen and its deshielding effects. So in this case, the split that we're working with here is going to be 0 neighbors because we do not account for the CH2, plus 1 is going to be equal to 1. So the n plus 1 rule here says that this should just be a singlet. All right, and that would be the general NMR spectrum that we would expect for ethanol. And if you question it, I would encourage you to pause the lecture and go look up ethanol on YouTube or Google or anything like that and try to pull up an NMR for it. Yes, you may see some different shifts in terms of where the actual numbers are slightly. They shouldn't be way off, but you should certainly see that type of integration pattern, and you should also see the splitting pattern. That would not vary when we're looking at these. All right, so that is a way that you can predict NMR based on looking at your compound. Now, I will do one more of them here, and then at that point we're going to bring up some actual NMR spectrum, and we're going to analyze them and look at them in terms of structure. So let me clear this and I'll bring up one more example. Okay, so the next example that I want to take a look at is benzaldehyde. So benzaldehyde is going to be a benzene ring, and this benzene ring is going to have a C double bond O H coming out of it. So that's benzaldehyde. This one we're going to go ahead and put up on our spec as well. So here's 0, 12, and a rough 6. And let's discuss where we would expect certain things to appear. So, first things first, we've got some hydrogens that are coming off of this compound here, and we don't want to forget about them. So these are all hydrogens coming off of the aromatic. Okay? And when you look at these, they are all in different positions relative to the benzaldehyde and to one another. And so you're really going to get a huge cluster of splitting in the aromatic region. This is referred to as a multiplet. So sometimes we have triplets or doublets or singlets. You can also have a multiplet when you have a large overlapping of peaks in a small area that are all sort of have a sloppy splitting pattern and overrun with one another. Okay, and then we will also have, and it is important to note, the aldehyde proton right here. Okay, so this one probably won't take quite as long because we just have to assign 2 peaks, which would be the aromatic multiplet and then the aldehyde peak. So the aldehyde, if you recall, is very, very deshielded, and it's going to appear roughly around 10 ppm. Okay, so we'll mark that down here. And if I take a look at it, okay, so there's 10 ppm. It's going to integrate to 1 hydrogen. Actually going to change that. That looks like an 8. Integrate to 1 hydrogen. And then the splitting, because it's next to this carbon-oxygen group, right, would be 0, because there's 0 protons there, plus 1. So I would expect to have a singlet there. All right. So that would just be 1 signal right there, and it should integrate to 1 hydrogen. So the aromatic, right, if you take a look at this, it can start to be a mess considering that aromatic protons, okay, especially if there's only one group influencing them here, are all going to appear in a relatively close or same region to one another. And then you've got some protons splitting with other protons because they're directly next to them, but they're all going to be splitting on top of one another. So what happens in a case like that, okay, is that we take all of these guys and we assign them to a multiplet. So we would see a multiplet at approximately, and again we're making an estimate here, let's say around 7.4. Okay, so at 7.4, I would see a large mess of peaks that would be here, sort of all overlapping together. And this multiplet would integrate to 5, because there's a total of 5, right? 1, 2, 3, 4, 5 protons. And the splitting pattern would be a multiplet. So that would be the rough structure of benzaldehyde. And following this type of structure, meaning an aromatic structure, I'm going to clear this now and I'm going to put up a set of NMR spectra that deal with some aromatic compounds. And we're going to take a look at some of the differences between them. So let me clear this real quick and we'll be right back to start looking at some spectra and we'll compare them to their compounds. Okay, so what I have brought up here are several general NMR spectrum, and you can see, looking at each spectrum, that there are some aromatic peaks present, and we want to kind of go through and look at the difference that we see between these. So remember that the aromatic peaks should always show up somewhere between 6.5 and 8 approximately. There's a little bit of buffer room, but in general that's where we're going to find them. So if you take a look here, okay, there are aromatic peaks in the, I'd say like 6.7 to 7.2 region for the aniline. And then when we look at this NH2 group, right, specifically the protons on this NH2 right there, they appear right here. And remember, I said that they would be similar to alcohol protons if we were looking at them. And that is within the range of where we would expect to find alcohols for a 2.5 to a 5.0. And so that falls right in the middle of that, and those would be the protons associated with this NH2 group. Right? Now, benzoic acid, and if we were to draw out this group, right, it would be COOH. Well, the benzoic acid, we said that carboxylic acids are going to be very, very high, somewhere between 11 to 12. And so you can see that that is where we indeed find the peak for the acidic benzoic acid proton. And you can see that we have the aromatic peaks probably around a 7.4 to an 8.2. Now, one of the things that's interesting here, okay, is that the NH2 group is going to be considered, when it's on an aromatic ring, to be an electron donating group, whereas a benzoic acid group, when it's on a ring, would be an electron withdrawing group. And so what we can see is, in the case of the electron withdrawing group, we find the aromatic protons are approximately a 7.6 to an 8.2, whereas when we have the electron donating group present on the ring, we find that these electrons are, or these protons, excuse me, are somewhere in the region of 6.6 to 7.2. Okay, so the electron withdrawing group performs more deshielding, and when things are further deshielded, we expect to find them further downfield. And so that's just evidence of that happening right there. Okay. Now, if we come down here, here are two more examples. We have benzyl alcohol and we have phenol. Right? So with benzyl alcohol, you've got a couple things here. The first is this peak right here, right above 7 ppm, would be the aromatic, right? And then if we continue to look, right here, what is this big peak in the middle? This would be the CH2 group, right here, that is attached to the alcohol, and that would give the prominent peak here. Okay, and then this small peak, and many times alcohols will have smaller peaks compared to their alkyl counterparts. This small peak right here would be the alcohol. So we'll do that in a different color here. This one right here would be the alcohol right here. Okay. Now what about phenol? When we get to phenol, we just have the alcohol without that CH2 group, and it's directly attached to the ring. So you notice when the alcohol is directly attached to the ring, it pushes it further downfield. So now our alcohol peak, instead of being around a 3.3, is around a 5.3, right? And then the ring also has its peaks in the 6.8 to 7.2 region, okay? Again, the alcohol, in the presence of the ring, because of its lone pairs, it donates electrons into the ring. It's an electron donating group. So again, look at this range. We have a 6.8 to 7.2. So we are dipping below the 7 mark when we have these electron donating groups present. Okay, so up here, we said when it was the amine, it's a 6.6 to a 7.2. So that is a look at some of the different variations that you could come across. These were all aromatic compounds, and they were fairly similar to one another. They had nitrogen or oxygen groups that were pretty close to the ring. So you can see the different variations, even when you get into the aromatic range, based on deshielding or shielding. And notice that many of these just appear as a giant cluster of peaks. Okay, so there is some separation between some of them, but those are very characteristic multiplets that are happening in the aromatic region. So I'm going to bring up one additional spectrum that we're going to take a look at in a little bit of detail. I will put the structure up next to it, and we will discuss where each peak is. And then once we're done with that, we will move into some of our practice. Okay, so this new spectrum that I pulled up is the one that we are going to focus on now. And this is a proton NMR spectrum for the molecule 2-ethyl-2-butanal. So this is going to be an aldehyde, and I'm going to draw the structure here, and then we want to look at how each peak is associated with this. Okay. So here's the structure. The structure would look like this. It's but, so you've got 4 carbons, and because it's an aldehyde, you're going to have a terminal aldehyde in position 1 here, and in position 2, that's where you would end up finding your double bond. So from 2 to 3, you would have a double bond, and then you would also have in that position 2 an ethyl group like that. Okay, so that's the structure that we're working with here. Now, I'm going to draw it out in a bit more detail in a minute, but I want us to first of all count the number of peaks that we should expect, not including splitting. So I should really say the number of signals is what we're looking for here. So let's go through and try to identify it, and then we can talk about the splitting and everything else. So here is a CH3 group. That's going to be 1 signal. Here is a CH2 group. That's going to be another signal. There would be a hydrogen coming off of this double bond, so that would be a 3rd signal. There's a CH3 group here. That would be a 4th signal. And then the aldehyde right here would be a 5th signal for that aldehyde proton. Okay. So how many signals do we see here? We see 1, we see 2, and this is, I'm going to help you guys here a little bit. This right here, if we can squeeze it off, that's its own signal. These two are very close, they're overlapping with one another almost. Okay, but this is clean enough that we can call this 2nd signal, this the 3rd signal, we've got a 4th signal, and we've got a 5th signal here. All right, so that's where we're going with this. We've got 5 different signals, and we need to figure out each one and assign it. And I'm going to, like I said, bring out a more structured version of this molecule in hopes that we are going to assign each one to each part of the spectrum. So let's start by drawing this out in some detail. And I'm going to erase this one now that we have the general idea. So what we're going to be working with here is something that looks like this. Here's the aldehyde. The aldehyde is going to be attached to a carbon here, and this carbon is going to be double bonded to another carbon that is going to have a bond to a CH3. Okay, so there's our main chain. This carbon has a hydrogen coming off of it, and then moving up here just a second, this carbon has a CH2 and a CH3. That's where the ethyl group comes off of it. Okay, so this is the structure that we're working with here. This should be a CH3, excuse me. So let's knock out some of the easy ones first. That's what I would say. So if you were to look at this and pick one out, the easiest one, the low-hanging fruit, so to speak, I would say would be the aldehyde proton, because we know those always show up in the 9 to 10 region, and so that would be this guy right here. So this is going to be the aldehydic proton that we find attached to that structure. So that knocks that out. All right, now the next thing that we have here, let's take a look at this. Okay, we can kind of reverse engineer some of this. This guy right here, okay, is appearing as a quartet. So that means if the n+1 rule holds, its neighbors should have a total of 3 protons, right? Because 3 + 1 is 4. So if we're working backwards, we also look at the ppm. This is sitting around a 6.5, a 6.6, somewhere in there. And if it's going to be a number that high, I would either expect it's going to be aromatic or it's going to be vanillic. And we do not have an aromatic compound here, but we do have a vanillic proton, right? This vanillic proton, just by the ppm estimation alone, would be the candidate. But let's just confirm the splitting here. This proton is next to a carbon that is next to a CH3, and it's next to a carbon that just is another carbon. So we said 3 neighboring protons, right? 3 plus 1 is going to be 4. So that is good to go. Now, the next thing we have is a quartet. And this quartet can be seen right here. Okay, that's the tip of it. It kind of goes here and here. There's a total of 4 peaks there. I'm hoping you guys can see. All right, so this quartet means, again, it should be for something that has a neighboring of 3 protons, and this is just slightly above 2, right? This is about like a 2.3 or thereabouts. So there's only one thing that would really make sense here. If you take a look at what's left, you've got the 2 methyl groups, right? Each of the CH3s, and you have the CH2. Well, the first methyl group here, if I were to take a look at that methyl group, its neighboring proton is only 1, so I couldn't get a quartet out of it. And if I look at this methyl group, its neighbor only has 2, so I could only get a triplet out of it. So hopefully you see where we're heading here. What we really want is this guy right here, because this methylene group has a CH3 and a carbon as a neighbor, so it's got a total of 3, plus 1 would be 4 for the quartet, and so this is going to be the most likely candidate for those peaks over there. All right, and then bringing it home for the last 2, if we were to take a look at them, right, where would this methyl show up? Well, this methyl is not as close to the double bond there as the other methyl is, and so we would expect it to be more shielded, plus we would expect it to have a triplet since it's next to a CH2, right? Because 2 plus 1 equals 3. So that means this guy right here is the triplet. The other one is a doublet, and by default, although it still matches correct, we're going to have this last one right here is going to be this guy right here. Okay? So hopefully you're getting the idea of the splitting, you're getting the idea of the ppms and the shielding and deshielding as we've worked our way through these examples here. All right? So the next thing I'm going to do is bring up some of these multiple choice questions. We're going to go through a couple of these practice questions, and then we will do a brief summary of what we've learned here, and we will go ahead and wrap up the part 2 of NMR spectroscopy. So give me a second to bring these questions up, and then we'll take a look at them. Okay, so I've now brought up the questions that we're going to use for practicing here. So number 1, which compound would be most likely to show a singlet between 2.0 and 3.0 ppm on a proton NMR? So you can see there's 4 choices here. Only one of these should give a singlet in that mentioned area. Number 2, which of the following order of proton sets goes from shielded or upfield to deshielded downfield? So just to be clear, when you're ranking these proton sets, you want to have the one that is at the lowest ppm, or for this upfield, first, and then the one with the highest ppm, or the one that would be most downfield, as the last option when you're working on that. So you can analyze that structure and figure that out. And then number 3, I'm going to leave this up here for a second so you can pause and take a good look at it if you need to. The following NMR spectrum is representative of, and this is an NMR of a certain amino acid. So the choices here are glycine, aspartic acid, phenylalanine, and tyrosine. So you're going to have to pick from one of those 4 choices, and I will let you know with this one, it may seem easy at first, but you have to put a little extra thought into it as you start narrowing the answers down, so just be aware of that. So I'm going to scroll one more time through these questions just slowly so you have a chance to make any notes or pause the video at a certain point if you need to. So again, number 1, which compound would be most likely to show a singlet between 2.0 and 3.0 ppm? Number 2, which of the following order of proton sets goes from shielded upfield to deshielded downfield? And then number 3, take one last good look at this NMR spectrum. It's for a given amino acid, and the choices are glycine, aspartic acid, phenylalanine, and tyrosine. So at this point, why don't you go ahead and pause the video, work through those questions and attempt to answer them as best you can, and then you can unpause when you feel you're ready, and we will go through this together. Okay, so number 1, which compound would most likely show a singlet between 2.0 and 3.0 ppm? So what we want to look at here is how these structures are going to differ from one another, and ideally one of them will show a singlet in that region. So if we take a look at this, the compounds here are all aromatic. So we would expect somewhere in the 6.5 to 8.0 or somewhere in there ppm region, that every single one of these is going to have a signal somewhere in there. Now that leaves the individual portions or the functionalities that are coming off of the aromatic rings. A carbonyl, which is a C double bond O, does not have any protons, so we don't need to worry about that. But as you can see, we do have sets of protons outside of that. So we have benzoic acid, we have the acetophenone here, which is the methyl ketone, we have benzaldehyde, and we have a acid chloride group here. So of the bunch, there's a couple of these that you can get rid of, and it should narrow down fairly quickly. So number 1, D, right here, cannot be an option, because outside of the aromatic protons, this chlorine does not have a proton associated with it, and therefore we would not see any additional signals outside of the aromatic signals. Now, for the remaining 3 that we have here, we've got the CH3 group, we've got the OH group, and we've got the H right here. So if you look at this, this is an aldehyde. An aldehyde is going to be around a 9 to 10 ppm. So that is much higher than the 2 to 3 that the problem is suggesting. We can eliminate that. And the benzoic acid here, remember that carboxylic acids have an approximate 11 to 12 ppm. So this one should also be out. That leaves choice A, and if you remember the trends that we went through, a methyl ketone, which is what this is, should show up anywhere in like the 2 to 2.5 region. So this is the most likely candidate for where we would find a peak between 2 and 3 ppm for question 1. So question 2 says, which of the following order of proton sets goes from shielded upfield to deshielded downfield? So we want to take a look at this in a little more detail. I'm going to draw this out with some explicit protons shown. So this is a CH2, this is a CH2 here, here's the chlorine, and then down here we have a CH3. All right? So hopefully you can identify and see that the most deshielded sets are going to be between these two. And that's because they are directly next to or attached to the electron withdrawing groups. So heavy deshielding is going to occur for both of those methylenes. And if we were to consider which one would have more deshielding, it's really a debate over which one has more electronegativity nearby. And chlorine is slightly more electronegative than bromine. It's got a larger partial negative, and so it's going to create a larger partial positive on this methylene group here. So this one, which is number 3 over here, okay, should be the most deshielded of the bunch. Now, that's going to mean that number 1 over here would come in second place in terms of deshielding. So this would be very deshielded. The bromine one that's right here would be somewhat deshielded in comparison to the chlorine. And then we have the methyl group and we have the CH group. So keep in mind that when you have a methyl and you have a CH, in general, methyls are going to be more shielded than CH groups are. And then on top of that, the CH is closer to the bromine and chlorine than the methyl is. The methyl is another carbon removed from those electron withdrawing groups. So that would mean that when we get to the CH3, this is going to be the most shielded of the bunch. And then this would be lightly shielded in comparison. So there'd be some more deshielding going on with that CH group. So of the choices, how should we arrange this? Well, let's just go straight for the correct answer here because we've already ranked it. So 4 would be most shielded, then 2, then 1, and then the most deshielded, or the one that would have the highest ppm, would be number 3. And so we see that answer B is correct here. 4, 2, 1, 3 would be the order based on the analysis that we just did. All right. Now the following NMR spectrum is representative of one of these amino acids. And if you remember, I said you have to be careful when you're analyzing this because 2 of them should be eliminated almost immediately if you're looking at the structures and you have a good grasp of NMR at this point. However, the other 2 you have to look at a little more carefully in order to determine what the correct answer should be here. Okay, so what I did here was to bring up a spreadsheet of all of the different common amino acids that we could potentially run across. So you're going to see the 4 that were potential answers in the multiple choice question appear here, and I just want to take a quick look at them as we're looking through this because I think it might be beneficial. So notice that all of the amino acids are going to have the NH3 group here. So depending on the pH, it might be NH2, it might be NH3+, but every single amino acid is going to have that basic grouping, right? Along with the carboxylate grouping, which we can see over here. Now, we're primarily concerned with this because this is showing protons, and on a proton NMR, we would expect peaks to show up there, right? So that's not going to be of any massive use to us if we're expecting that all of the amino acids would have that. All of the amino acids are also going to have this CH functionality. Now, what's going to differ is the other portion or the other chunk, the side chain that's coming off. So one of the options was glycine. And in that case, we have this hydrogen here. So this would just become a CH2 group that we would expect to see in addition to the NH3. And one of the other options that we had going down and working our way through this is phenylalanine. Now, phenylalanine has a CH2 group with a phenyl group attached. So this is important because the phenyl group right here is going to provide a different type of NMR signal than I would expect to just see from regular alkyl groups like a CH2 or a CH group. So keep that in mind. One of the other options was tyrosine. Tyrosine also has a very similar functionality, right? And we'll bring that up again in a minute as we're looking. And then we have this OH in addition. So that'll be important if we want to discriminate between tyrosine and phenylalanine. We should see one additional peak for the tyrosine that's representative of that alcohol. It should be a singlet. And then finally, if we come over here to look at the acids, we have the aspartic acid form here. This has a CH2 group, but it also just has another carboxylate group. So we can see that 2 of these are going to carry aromatic regions, whereas the other 2 are mostly just going to be alkyls, and we would have to determine based on the peaks and the splitting what we would expect there. So keep that in mind as we move forward and we start analyzing this problem. And I will redraw some of these structures as we move on here. So let's take a look. So the options here are glycine, aspartic acid, phenylalanine, and tyrosine. So if you come up here and you analyze the proton NMR spec for whichever amino acid this is supposed to be, there is one very important region, and this is how you should go about trying to look at NMRs, is seeing if you can see anything that really stands out and allows you to make an immediate conclusion. So right here, the only thing that would appear in this general region is going to be some sort of an aromatic ring. Now because of that, and this implies that we have an aromatic ring here, we can immediately get rid of glycine and aspartic acid, because neither of these are going to have any type of the aromatic compound if you were to look at their individual amino acid structure. Now when we look at phenylalanine and tyrosine, these are both aromatics, and so we have to look at this with a little bit more scrutiny. So what does phenylalanine look like, and then what does tyrosine look like? Well, phenylalanine is going to have the aromatic ring. It has a methylene group, so a CH2 as part of the side chain, and then you get to the main portionality of the actual amino acid, right? So all of the amino acids have the carboxyl group and the amine group. Now keep in mind that depending on the pH that this is at, we could potentially lose this proton here, right? And we could be in the carboxylate form. So what we want to look at here is what sort of signals would show up. Well, we have the aromatic ones. So that will be the obvious 7 to 8 region that we were discussing. There's protons, all in there. Then we have this CH2 group, and we have this CH group as well. So you would have a set of 3 signals for this, and we do indeed see 3 signals here. It may look like 4, but this splitting right here is really one signal that's grouped together. If you look at the baseline, it doesn't really separate. You've got a second one here, and then you have the third one as the aromatic. So that seems like it would be a good candidate. In terms of the positioning, this CH group is by 2 very electron withdrawing groups that are going to influence with deshielding. So we would expect that that CH group is potentially this one at 4 ppm right here. And then the CH2, which is between a CH and an aromatic ring. The aromatic ring is certainly going to provide some deshielding, as well as the other groups that are another space away, but we would expect that CH2 to have a slightly lower ppm and be slightly upfield. So this seems like a good choice. Now what could be tricky about this? Well, if you're looking at tyrosine, tyrosine has almost the exact same structure. However, it has an OH group, hydroxyl group that's coming off right here. And so the main difference, these are going to look almost identical to one another. This hydroxyl group is the main difference here. And because the hydroxyl has a proton, you should see one additional peak involving that proton, probably somewhere between the 4 to 5 ppm range. You would find an additional peak, a singlet, that is going to associate with that proton. So because we see a notable absence of that additional peak here, it could not be tyrosine, and phenylalanine is the correct choice for the amino acid that this corresponds to. So hopefully these questions made sense to everybody, especially now that we've gone through, we've seen some practice and some examples here. So we will clear the board and we will briefly wrap up with a summary of important points to take away with regarding NMR. All right, everybody, here's our summary for the second NMR portion and what we discussed during this second lecture. So remember that it is very important to attempt to know the basic trends for parts per million when you're analyzing these spectrum. So examples here, we went through a detailed list. You can go back to that and take notes and make a table for yourself. but a couple examples here. Alkyl methyls should appear around 1 ppm. I think the range we gave was like 0.7 to 1.3, so these are approximations. Methyl ketones, 2 to 2.5, aromatics 6.5 to 8, aldehydes 9 to 10. Those, again, are some examples. We talked about others like allylic and vanillic and aromatic toluenes and things of that nature. But having a good grasp on where some of these should fall will help you eliminate choices very easily when you get ready to start looking at the multiple choices. Utilize the N+1 rule when you are predicting splits. So if there's any question asking you about splits, or you need to analyze how peaks are being split, you can go through and you can look at all the spin states like we did in the first lecture, but as I mentioned earlier in this second portion, you really want to be utilizing the N+1 rule. It's the quickest way and the most efficient way when you are under pressure and time constraints. Remember that splitting is going to refer to the number of neighboring protons, while integration values are going to account for the protons of the current signal. So, one more time, do not end up thinking, oh, I see a triplet, so therefore this must be a CH3. The splitting has to do with the number of neighboring protons. It does not have anything to do with the current number of protons for that signal. That's what the integration is there for, right? And the ppms are there in order to help you figure out approximately how shielded or deshielded these protons are, which is telling you something about their environment, the way they're set up in the chemical structure. Then we have this note here. More electronegative groups will deshield electrons from the surrounding nuclei, and because of this, those nuclei are more exposed to the magnetic field, so this will cause higher ppm values to appear. That's what we were just talking about at the end of the last point there. And then finally, and a very practical point here, you saw in the last of the examples we were doing together, look for easily identifiable peaks, because that can give way to easy choice elimination. So like we did with the amino acid structure, we took 2 of them out immediately because those amino acids did not contain any type of aromatic peaks, so they were easy ones to toss out and bring it down to a 50-50 shot. And then that's where we spent more of our time analyzing. Okay, it would not be ideal to start with a spec and say, I'm going to pull apart every single peak, I'm going to look at it, integrate, make sure that the ppms all match what they're supposed to, and start guessing at structures. No. Take a look, say, oh, I see an aldehyde, oh, I see an aromatic peak, anything of that nature, so that you can immediately attempt to shave off some answers if they are not correct. So that's going to finish NMR Spectroscopy Part 2, and you should have a good grasp on NMR Spectroscopy after these 2 lectures that we've had. So that will conclude for MCAT ACE, and we will see you guys in other lectures.